All right, so let's take a look at another scenario of forces acting in two dimensions. So, when we're dealing with inclined planes, just like before, we don't care about the horizontal dimension, we don't care about the vertical dimension. Rather, the dimensions that interest us are the dimensions parallel to the incline and the dimensions perpendicular to the incline. So, whether this thing is moving up or down, we do know that gravity, right, the weight of the object, is straight down. Now that doesn't help us because it exists in both the parallel dimension and the perpendicular dimension. So what we always need to do is we need to break it up into its component pieces. Right? So we could call this FG perpendicular. We can call this FG parallel. Now, theta, the angle of your incline, is going to be the same as this angle here, just like before. So when we're examining um, forces acting on an incline, we need to find FG parallel and FG perpendicular in terms of FG. So if we do our trigonometry, right, we can find that FG parallel is equal to FG, right, your weight, times the sine of your angle. While FG perpendicular is your weight, mg, times the cosine of your angle. Now, one big thing to recognize here is that FG parallel is always pulling down, right, down the slope. And that makes sense, right? That's the only reason a slide works, right? It's because you have this this parallel component of the gravitational force pulling you down, right? The steeper this angle gets, the closer this angle gets to 90, the greater FG parallel becomes. The closer this angle gets to zero, the smaller FG parallel becomes. Now, one thing to keep in mind on an incline, and there are tons of multiple choice questions out there that are looking to trip people up on this, is figuring out what the normal force looks like. A lot of people want to put the normal force going straight up, like this. Well, you can do that. Because again, think back to when we discussed the normal force. Normal in math means perpendicular, right? And so the normal force is a force that's perpendicular to the surface. So your normal force is perpendicular to the surface of this incline. So typically you don't have acceleration in the perpendicular on any of these incline problems. So typically your normal force is going to be equal to your perpendicular component of the gravitational force. So here's your basic template for these problems. Let's go through a couple together. So if you look at the 2D force problems that were posted up when we discussed equilibrium, um, these last three are all inclined plane problems. So let's look at number 4 together. In this case, we've got a farmer. He pushes a 40 kilogram pig up a muddy hill at a 52-degree incline with constant velocity. The force of friction is 35 newtons. How much force is the farmer exerting on the pig? All right, so let's start, like we always do, with the free body diagram. We've got our pig. We know that pig has a mass of 40 kilograms. We know that theta, the incline, is 52 degrees. He is pushing it uphill at a constant velocity. So that term should jump out at you. Constant velocity means it's in equilibrium, meaning acceleration is 0 meters per second squared, and your net force is 0 newtons. All right, we know we've got a force of gravity straight down that we can break into its component pieces, where this would be mg sine theta, and this would be mg cosine theta. We know we've got a normal force, again, make sure it's perpendicular to the surface of the incline. He's applying a force uphill, and he's encountering 35 newtons of friction. So 35 newtons. So this is our free body diagram. And we want to know applied force. Now, just like always, best place to start, or the only place to start, is a statement of Newton's second law, right? A net force statement. So in this case, right, we're interested in the perpendicular. So we know the net force in the in the parallel. The net force in the parallel is 0. Well, what forces do we have in the parallel? We've got applied force, we've got frictional force, but we also have this parallel component of the gravitational force, which is pulling downhill. So we've got applied force minus friction minus that parallel component of gravity, all equal to 0. So your applied force would be equal to friction plus that downhill parallel component of your gravitational force. So applied force would be 35 newtons plus 40 kilograms times 9.8 meters per second squared times the sine of 52 degrees. So your applied force in this case would be equal to 343.9, so let's call it 344 newtons. Alright, so again, it's not anything new we're doing. We're just, instead of examining the horizontal and the vertical, we're examining the parallel and the perpendicular. So let's take a look at one more example together. So number 5 on that, we have a 90 kilogram man slides down a muddy hill at a 25-degree incline. The force of friction is 20 newtons, and we want to know what's the man's acceleration. So again, we want to start with the free body diagram. So we've got our incline. We've got an angle of 25 degrees. We've got our guy sliding downwards. We know that he has a mass of 90 kilograms. We know he encounters a frictional force of 20 newtons. We want to know acceleration. There's a normal force. There's a gravitational force. And again, we can break that gravitational force into its component pieces. So, good place to start is always finding what your FG parallel and what your FG perpendicular are. So again, FG parallel is force of gravity times the sine of theta, and perpendicular is FG times the cosine of theta. And so we get that FG parallel, your parallel component of the gravitational force, the one that runs downhill, is 372.8 newtons, and FG perpendicular is 799.4 newtons. Now, again, start with looking at Newton's second law, where in this case our net force in the net force in the parallel is equal to mass times acceleration. Now, the net force in the parallel is going to comprise of friction and this downhill gravitational force, the FG parallel. So, FG parallel minus force friction equals ma. Now, you may have noticed in the last problem, I made uphill positive, and in this problem, I'm making downhill positive. Rule of thumb is it makes your life easy if you make whichever direction this object is going your positive direction. That way you don't have to worry about all of these negatives. Right? So if it's going downhill, downhill is positive. It's going uphill, uphill is positive. So if we rearrange this, we get Fg parallel minus force friction over mass is equal to acceleration. So your acceleration is equal to 372.8 newtons minus 20 over 90 kilograms. And so you get an acceleration of 3.92 meters per second squared. Right, so again, nothing new. You're just examining the net force in the parallel and the perpendicular rather than the horizontal and the vertical. Now I'm attaching a list or a set of problems that deal with this. I'll post the key here tomorrow. Yeah, let me know if you have any questions, and see you in the live sessions.